Hello, friends, and welcome back to the channel. Today, we are kicking off Class 9 Science, Chapter 8, Journey Inside the Atom. I'm so pumped to get into this explainer because we're literally looking at the blueprint of the universe. It's going to completely change how you view reality. So let's jump right in.
Have you ever stopped to think about what everything around us is actually made of? Seriously, take a second and look around. Your mobile phone, the book on your desk, the water you drink, the air in the room, even your own body. What is the fundamental building block of all that stuff? Well, the ultimate answer is atoms. In this explainer, we're going on an exciting journey deep into the hidden world inside those atoms. Here is our roadmap for today. Number 1, roots of atomic theory. 2, Thomson and Rutherford models. 3, Bohr's atomic blueprint. 4, the subatomic particles. 5, atomic number and configuration. And 6, valency, the combining capacity. Let's start with Section 1, Roots of Atomic Theory. To see where the whole concept of the atom started, we have to go way back. And it's actually amazing how old this idea is. About 2,500 years ago, the ancient Indian sage Acharya Kanada proposed that matter is made of tiny, indivisible particles he called parmanu. Around the same time in ancient Greece, philosophers Democritus and Leucippus had a similar realization. They coined the term atomos, which literally means indivisible. Fast forward a bit to the 1800s, and John Dalton formalizes this into his atomic theory, stating that all matter is indeed built from atoms. Now, for a long time, Dalton's idea of a solid, unbreakable atom was the absolute truth. But, as we'll see, science is always evolving.
Moving on to Section 2, Thomson and Rutherford models.
So in 1897, J.J. Thomson makes a massive breakthrough. He discovers the electron. Suddenly, the atom isn't so indivisible anymore. To explain this negatively charged particle, he proposed the plum pudding model. Thomson suggested that a positive charge was spread all over the atom, and the negative electrons were just embedded in it, kind of like pieces of plum stuck in a pudding. It was the very first real attempt to figure out what the inside of an atom looked like.
But in science, you always have to test your theories. Enter Ernest Rutherford and his famous gold foil experiment. Rutherford fired a beam of alpha particles straight at a super thin sheet of gold foil. And his observations were totally mind-blowing. First, the vast majority of the particles went straight through, as if nothing was even there. Second, a few particles were slightly deflected off their path. But the craziest part, an incredibly tiny fraction bounced straight back toward the source. That completely shattered Thomson's plum pudding model.
So, what did Rutherford conclude? Well, since most particles passed right through, he realized that an atom is actually mostly just empty space. But those few particles that bounce back, they had to have hit something incredibly dense and positively charged. This led to his groundbreaking conclusion. Right at the center of the atom, there's a tiny, dense, positive core, which we now call the nucleus.
Let's look at Section 3, Bohr's atomic blueprint. Now, Rutherford's model was a huge game changer, but it wasn't perfect. People wondered, why don't the negative electrons just get pulled into the positive nucleus and collapse the whole atom? To fix this, Niels Bohr stepped in with some strict traffic rules. He showed that electrons don't just float around randomly, they revolve around the nucleus in fixed energy levels, or shells. And here's the cool part, they're dynamic. They can jump from one shell to another, but they must gain or lose specific amounts of energy to do it. This fixed shell system is exactly what keeps the atom stable.
Next up, Section 4, the subatomic particles.
So let's lay out the three main subatomic players we found inside the atom. First, the electron. It has a -1 charge and lives outside the nucleus in those energy shells. Then we have the proton. It carries a +1 charge and is locked firmly inside the nucleus. Finally, there's the neutron. It has 0 charge, so it's completely neutral, and it hangs out in the nucleus right alongside the protons. The discovery of the neutron was actually the missing puzzle piece that let scientists finally make sense of atomic mass.
Which brings us to Section 5, atomic number and configuration.
Let's use carbon as a concrete example to make sense of this. Every element is defined by its atomic number, which we call Z. This is simply the number of protons it has. Carbon has 6 protons, so its atomic number is exactly 6. But what about its mass? That's the mass number, or A, which is the total of the protons plus the neutrons. For carbon, 6 protons plus 6 neutrons gives us a mass number of 12. Now, how are those electrons organized? We know they live in shells, but there's a strict limit to how many can fit. The closest shell, the K shell, holds a maximum of 2 electrons. The next one out, the L shell, can hold up to 8. The M shell holds up to 18. Take oxygen, for example, which has 8 electrons in total. We drop the first 2 into the K shell. That leaves 6, which fit perfectly into the L shell. So oxygen's electronic configuration is simply 2, 6.
Finally, section 6, valency, the combining capacity.
So what exactly is valency? Basically, it's an atom's combining capacity. Think of it like the number of hooks an atom has available to grab onto other atoms. This dictates entirely how it's going to interact and bond to form compounds in the real world. Without valency, atoms would never connect, and complex stuff like water or the cells in your body would literally never exist.
Let's look at a few quick examples to lock this in. Hydrogen has a valency of 1. It's got 1 hook. Oxygen has a valency of 2, so it needs to make 2 connections. And carbon? Carbon has a valency of 4. Because it can make 4 different connections at once, it's a phenomenal building block. That's exactly why carbon is the foundation of all known life. And these valency numbers all tie directly back to those electronic configurations we just looked at.
And that wraps up our atomic journey today. We've covered a ton of ground. Acharya Kanata and Dalton's early theories, Thomson's model, Rutherford's gold foil experiment, Bohr's energy shells, the subatomic particles, atomic and mass numbers, configurations, and finally, valency. Always remember this. Everything around us is made of atoms, and understanding atoms helps us understand the entire universe. But think about this. If Rutherford proved that atoms are almost entirely empty space, and you are made of atoms, does that mean you were mostly empty space too? If you enjoyed this explainer, be sure to like, share, and subscribe for more. Until next time, keep your curiosity alive.